Hi, Errichto here. We're solving two arrays and sum of functions, problem from Codeforces. We're given two arrays A and B, both of the same length n, and we want to rearrange elements in B in order to minimize some function. Let's see on example what is that function. We have some B, 10, 20, 30, we change the order of elements, and then for each interval, for example for this taking first and second element, we compute the sum over products of corresponding elements of A and B, here 5 times 30 plus 4 times 10, and we take the sum. Here the sum would be 190, this is 150 plus 40. We take that sum, we compute that sum for each n interval, intervals of size 1, of length 1, 2, and so on up to n, and we take the whole sum of those sums. Here we would get 910. Our goal is to minimize the total sum, to rearrange elements in B to minimize the sum. On second example, here we have for this interval 1 times 4, which is 4. On this interval we have 6, and this total interval is 1 times 4 plus 3 times 2, which is in total 10, and then we take the sum of those sums, which is 20. This is the sum that we should print, minimized, after rearranging elements of B. And we should print the answer modulo some prime number, because otherwise this would exceed even long type. And it makes the problem a little bit more difficult, but we will talk about it later during the implementation of a solution. When problem isn't trivial, it's good to first solve some easier version of it. Here n is up to 200,000, so during a contest I would either first try to solve it in just any polynomial time, because naive brute force would be n factorial times something if we want to check all the possible orders of B, and n factorial is way too big. So maybe we can try to solve it for like n up to 100, just any polynomial solution. Maybe we should look at some examples with n equal to 2 or 3 and see what is the optimal order. Or maybe we should first consider some simpler function and solve a problem for that function. And I will choose this version here. And instead of iterating over all elements, I will try first just rearranging elements in B to minimize the sum over products AI times BI, forgetting about the intervals. If we want to just minimize the sum over products AI times BI, then I can see an example that it's better to rearrange elements of B in such a way that big element in B would be together with small element of A. I can see here that if I put 20 with 4 and 10 with 5, I get 130. It's better than putting 10 with 4 and 20 with 5. It can be proved below is a lemma that if we have those two elements of A, 4 and 5, where the first one is smaller, so I denoted them as lowercase and uppercase a, same with B, then this inequality holds. It's better to put small element of A together with big element of B and the other way around. You can pause a video now for a moment to think about this inequality, and now let's see the proof. I can move everything with A to one side, B minus B, and everything with uppercase A to the other side. And this is trivially correct for non-negative numbers with these inequalities that we know. Or I can even put everything to the right side to get 0 smaller equal A minus A, B minus B. And both these are non-negative, so the whole thing is greater than or equal to 0. This way we can also prove generally, if we have some elements of A, let's say not only 4 and 5, but 4, 10 and 7, and we have some elements of B, we should put the biggest element of B together with the 4, smallest element, like here 20, then second smallest element of A with second biggest of B, and so on. To minimize the sum of products, put big elements with small ones and small element with big ones. Otherwise, if we have a product of two big elements, the product will be huge. We already know how to solve a problem if we cared only about the sum of products. But the statement said that we care about the sum over all intervals, and in each interval we sum the products. Now let's think, if we fix the order and we have some product like A2 times B2, then in how many sums this will appear. Then we will know how many times it will be added to the total sum, to the answer. I know that it will be in this interval, just of size 1 containing second element, this one, and a few other ones. There is an easy formula to calculate that, because index 2 will be in all intervals that contain this index, so the start should be before that and end should be before that. The start of interval should be somewhere here, and the end of interval should be somewhere here. And the number of intervals that contain here index 2 will be 2 times 3, which is 6. 2 is the number of possible starts of an interval. The general formula will be I times, this is the number of possible starts up to position I, times n minus I plus 1. This is the number of possible ends, not earlier than I. This is the multiplier with which we add A2 times B2 to the answer, times A2 times B2. And we can use it to completely solve the problem. After rearranging elements of B, we want the following sum to be minimal. The sum over AI times BI, the product, times the number of times it will be added to the sum, I times n minus I plus 2. And it helps in sub-problems to group elements of some formula into two groups and then do something with that. It happens very often with some convolution and FFT. Here, of course, we have something easier. We can rearrange BI, and we know already some values AI. We also know values I and n minus I plus 1. So I will group together those three, and I will say that I minimize the sum over BI times this big value, AI times I times n minus I plus 1. And this is something I can compute for every I. Actually, I will just change AI to this value, and then I want to minimize the sum over AI times BI, where AI is that new value, after multiplying it by I times n minus I plus 1. Something that we already know how to solve, because we just match big values with small ones, for which we will need a sort. The implementation will be quite short here, and you can find it in my GitHub repository, to which the link is in the description below the video. We have some module in the problem, and I said I would talk about it a little bit more now. We read n, we read the array A, and while reading, we multiply AI by I plus 1 times n minus I. You can see here a small difference from formulas on the right, because I number in my code indices from 0 to n minus 1, since the difference by 1. We don't apply modulo here, what is very important. With constraints from the problem, this fits in long, and I need to not do modulo at this moment, because otherwise the sort would be changed. I want to sort by values, because I need to take big values of A with small values of B, and I don't care about modulo right now. I also sort B. Of course, the problem doesn't allow me to change the order of values of A, but I don't care about the order anymore. I want to just match elements of A and B in some way with each other, and now I can do whatever to do that. It's just about pairing them in some way. After using index this way, I now can forget about indices. This is why I sort A increasingly, B decreasingly, and now I can match them one by one. Or I could both sort increasingly and then take first of A with last of B, and so on. At the end, I take the sum over AI times BI, but first I here do modulo on AI, because this value is up to 10 to the 18 or so with constraints from the problem, and without modulo in this line I would here hit overflow. I take one modulo here and then answer plus equal the product and modulo of everything. At the end, print the answer. I hope you liked this video and see you soon. Bye bye.